Welcome. In this video we will be talking about pivoting and partial pivoting. So by the end you will be able to improve on the Gauss-Jordan algorithm by including pivoting when it is necessary, and you will be able to mitigate round-off errors by using what is called partial pivoting. So in a prior video we talked about the Gauss-Jordan algorithm, and now we're basically asking the question, what could possibly go wrong with this algorithm? So here's an example where already the augmented form of the matrix is shown. And if we would step through our algorithm, we would look at the first pivot position and we would find a 0 in that pivot position. So our very first step of dividing by this pivot value will fail. Now, if we encounter a 0 in the pivot position in a linear algebra setting, what do? Right? Well, we would just row exchange. We would pivot. Exchanging rows is what we would call pivoting. So in this case here, we would look at the 0 in the pivot position, and we would then look below this pivot position to find the first non-zero value. Right? So we start below the pivot, we would go below in the same column to find the first non-zero entry. In this case, this would be the number 1. And then we would exchange row 1 with row 2, and that would put a 1 in the pivot position, and then our algorithm could commence. So in general, let's say we are not working on the first row, but we're working on the kth pivot row. If the pivot in row number k is equal to 0, then what do? Well, we start with the row j just below the pivot row, and while we haven't reached the last row, n, right, number of rows was n, so while we haven't reached the last row n, and the entry in this column and that row is still 0, we would just go on to the next row by increasing the row number j by 1. And once we have found an entry that is not 0, we will then exchange row number k with row number j. Okay, so let's develop the MATLAB code for this. So the first thing we did was, if the pivot in row number k is equal to 0, then we will do something. So in MATLAB, that is just if C was the name of our augmented matrix. If C at position kk, that means row number k, column number k, is equal to 0, then we will do something. What will we do? Well, we start with the row j below the pivot row. So our row number j would be k plus 1, the next row after our current pivot row k. And then the word algorithm says, while we haven't reached the last row, n, and the entry is still 0, so that would translate into while j is smaller equal to n, and the entry c at row j column k is still 0, then we will increase the row number j by 1. So j is equal to j plus 1. So this while loop will exit if we find an entry in the pivot column that is not equal to 0. And then we have to exchange row k with row j. And I'm just going to write this as a comment in here for now. Okay, so this is the algorithm that would let us exchange rows if we find a 0 in the pivot position. So here's a challenge question for you. We now have to exchange rows j and k of the matrix C. Which of these MATLAB codes will do this for us? So the first option is C, the matrix C, of j, that's the row j, from 1 to p, so through all columns, all entries of that row j, is equal to C of k from 1 to p. And then we do C of k, so the kth row entry, is equal to the jth row of C. That's option A. Option B is that we do the same thing, but just flipped, right? So we first copy row j into row k, and then we copy row k into row j. Option C is, well, both A and B would work. And the last option, D, is that none of the above would work. So think about this for a little while and then click on the answer that you think is right. Okay, so the right answer is that none of the above code segments actually will exchange the two rows. And to illustrate that, let me try to visualize the individual rows by two different classes that are filled with liquid of different color. So let's say row number K is a glass filled by a blue liquid, and row number J is another glass that's filled by a yellow liquid. And let's just look at what that first line of code of option A does. So it does basically take the row K, take that glass and pour it into the row number J glass. So let's take that, we pour it into that, and now row number J, that glass, contains just the content of row number K. So when we then go to the second line of code, where we copy the content of J over into the row number K glass, then we pour this in there and nothing really happens because both already contain the same content. And the net end result is that both of these glasses, both of these rows contain now blue liquid. We haven't done an exchange. So that doesn't work. Let's look at the option B. Let's reset everything. So we have blue in row K glass and yellow in the row J glass. And the first operation would be copy the row J into row K. So let's do that. We fill this up and now row K becomes yellow, containing the contents of row J. And then the second command copies the K content over to the J content. Both of them are already yellow. They just contain the original content of row number J and nothing else will happen. So neither A nor B actually would work. And then by elimination, it means that none of these choices actually would do the trick. So how can we exchange the content of these two rows, of these two glasses of different colored liquids that are filled to the brim? Well, it's a little bit of a trick question because we can't really unless we bring in an additional helper glass. So how do we use it then? Well, then we just take the content of row J and copy it over into our helper glass, and that would be in code that we set help from column 1 to column P is equal to the jth row entry of C from 1 to P in the column number. So now we've made a safe copy of the content of our row J. That means now we can copy the content of row K into row J, overwriting the content, the yellow liquid in there. That would be the code C of J from 1 to P is equal to C of K from 1 to P. And now we can, in the last step, take our saved storage help class and copy it over into row K. So the code for that is just that C of row K, all the columns from 1 to P, is equal to our help array or help class with all columns copied from 1 to P. So this would be the code snippet that then does the copying, the exchange of the individual rows. So that's the code snippet that goes now underneath the column that we had from the algorithm before, where we wanted to exchange rows K and J. So that is the code segment now that does what's called zero number pivoting, that we exchange rows if we find a zero in the pivot position. But what if there is no non-zero entry? Meaning we will hit the end, the last row, the row number n, before we can find a non-zero entry. Well, that means from linear algebra that this matrix A is singular, meaning it doesn't have a single solution. So that's a matrix that we can't really solve in this algorithm. Now, if you think about and look at the algorithm here, you might notice that the algorithm as presented here will actually generate an error message. And I've put here on the slide the code that you would need to put in there to catch that error message without the actual function then erroring out. You can say if j is greater than n, so if I've gone beyond the last row of the matrix before you try the row exchange, you would just print an error that this matrix is singular. But in all the matrices that we will encounter in this class, those matrices will fortunately not be singular. So what else could go wrong? Let's look at this example here, right? There are just some numbers. None of them is 0, so this matrix is not singular. The exact solution to this 2 by 2 system is that the x1, the first entry is 10 for x, and the second entry is 1. And you can kind of verify this by plugging in this exact solution into the matrix equation here. So 10 times 3 times 10 to the negative 4 is 3 times 10 to the negative 3. And if we add that then to 1.234 times 10 to the power 1, we actually get 1.2343 times 10 to the power 1. And you can verify this with the second equation as well, that this is the exact solution. Now, let's solve this, but we're only going to use 4 significant decimal digits, just to drive home a point. So the only thing that will happen in this matrix, if I round everything to 4 significant digits, is this first entry on the right-hand side, because that has 5 significant digits, and I'm going to round this to 4 significant digits, making it a 1.234 times 10 to the power 1. Now I'm going to solve this now using the Gauss-Jordan algorithm. And if I do this with 4 significant digits, what I'll have to do is, after every single operation, I will have to round the result of that operation to just 4 significant digits. And if you do this, you'll find that the solution is, the first value is 20, x1 is 20, and the second value is 0.9994. So if you compare that to the exact solution, while x2 is pretty close, x1, if you compare 20 to 10, is widely off, right? It's really wrong. So why is this result so wrong, even though I have 4 significant digits available in my math? Well, the key lies in this pivot entry that is in the 1, 1 position of the matrix. And this value, if we look at it, 3 times 10 to the negative 4 is a small value. And the first operation of the Gauss-Jordan algorithm goes in and divides by this pivot entry. So what the very first step of the Gauss-Jordan algorithm does is it divides by a small number, which means the entire row, the entire first row, is divided by a small number, which makes all the other values in this pivot row large. Right? We divide by something 10 to the negative 4. That first value there is around 10 to the power 5. So those values will be large. But what do those values do? Well, those values are multipliers to generate zeros in the other columns, in the other pivot columns, when we get to generating the zeros in the pivot columns. So we have large multipliers, which means that any round-off error that we might have, because we only have 4 significant digits available, now gets multiplied by a very large value, amplifying this round-off error. Which means that the underlying culprit of this very wrong result lies, or is, that small pivot that we used. That is the start of the entire problem process. So we should try to avoid having small pivots altogether. So is there anything we can do about this? Can we avoid a small pivot? Well, fortunately, yes, we can. We just have to row exchange. We have to pivot. So because we always have a division by the pivot value in our algorithm, this pivot value should be as far away from 0 as possible. Okay, so what we're going to do is we're going to always exchange the pivot row number k against the row with the largest possible absolute value in the pivot column. So we will always strive to take the largest possible pivot value. But in our algorithm, we can only do row exchanges with rows below our current pivot row. And that, by the way, includes the pivot row, right? We can exchange the row with itself if that pivot entry in this pivot row just happens to be the largest possible absolute value. So the task now for MATLAB, if we want to code this, is how do we find the row j that is greater than our current pivot row k with the largest absolute value in the pivot column. And the MATLAB function that will let us do that is called max for max. And as input, right, also as the return of that max function, we will have two values. The first value is the actual maximum value in the input data to the function. That is the value of the pivot position that we want to have. And the input then that we put into the function is the column, the pivot column, starting with the pivot row all the way to the last row. And that's indicated by this index, that first index here into the augmented matrix C, where we start at the pivot column K and we go all the way to the last row N. So we're cutting out this one column out of our augmented matrix. So the result then, the second result on the left, is the position of this largest entry. And that position is relative to the start index of what the input array is into the max function. So this j value here is relative to the start index k, which means that if the kth row value, the pivot row value, would be the largest value, then the returned value for j is the first value, right? Because c of k, row number k, is the first row that we pass into the max function. So then what we'll have to do is we have to find the column number relative to the entire, the row number relative to the entire matrix. So that means, as an example again, if the pivot value ckk is largest, then j will be 1, but the actual row number that we want to get back is k, right? Because that is the row number relative to the entire augmented matrix. So how do we do this? Well, we just subtract 1 and then we add k. And then this j value will be the row number relative to the entire matrix. Okay, so we found j, right? The row that contains the largest possible absolute pivot value. And then all we need to do is we need to exchange row number j with row number k as we have done before, right? So here is that code snippet that does this row exchange. Now these 5 lines of codes replace the entire 0 number pivoting code snippet from before, because 0 can never be the largest pivot. So if we find a 0 in the pivot position, then our max function up there will always pick up a value that we will exchange into the pivot row that is larger than 0. If all the values are 0, well, then the matrix is singular and we can't solve it in the first place. And we call this pivoting using the largest absolute pivot column value. We call this partial pivoting. Okay. Now, does this really work? So let's go back to the example that we did before, rounding to 4 significant digits, where the exact solution was 10, 1. And without partial pivoting, our result was 20 and 0.9994. So if we now do partial pivoting in this example here, you'll see that the second entry here from the first entry in the first column here of the second row is actually much larger than the previous pivot value. So we would do a row exchange in this example here. So let's do this row exchange and again use 4 significant digits. And then the result that we will get is 9.996 and 1. So if you compare these results without partial pivoting and with partial pivoting, you'll agree that this result with partial pivoting is significantly better and closer to the exact answer. But there is, of course, still an error. We don't get the exact answer 10 and 1. And that's because we are doing only 4 significant digits, right? We have significant round-off error in the result. Now, let's go to the worst case possible. What if there is no good value to use for partial pivoting, meaning there are only small pivots in the pivot column below our current row K? Well, then unfortunately, our numerical solution is prone to round-off errors, meaning any round-off error will pollute our final numerical answer. Now, it would be great if there is a way to tell if a matrix runs into this trouble, if it is susceptible to round-off errors. And that's where norms and condition numbers come in that we will cover in a subsequent video. Thank you for watching.